Hello, today we'll be explaining squeeze theorem. So what is actually squeeze theorem? Squeeze theorem is when you take two other functions, like in this case where I'm taking f of x and h of x, and we're going to be using those two functions to squeeze a function in between them to be able to find their limits. So in this case, we'll be using f of x and h of x to trap and then squeeze g of x to be able to get its function. Here we have just trapped the function, and now once we squeeze it, we both know that both these functions are going to be approaching a certain point. In this case, we'll use x is approaching point A, and when they approach such said function, they must be equal to each other. So the limit must be the same. In this case, L. So let's visualize this. So f of x, limit f of x as x approaches A must be equal to L. Same thing goes for h of x. Limit h of x as x approaches A must equal L. Let's visualize this on a graph real quick. In this case, let's take f of x. There goes f of x. Let's quickly, h of x. It's my mistake. H of x, and let's take another function in between that. So let's call this one g of x. And let's take a function called h of x. So sorry about that. H of x. F of x, and then this would be g of x. So as you can see, these two functions are squeezing the function at point A. And at point A, that would mean this would equal to L, all at the same point. So let's quickly go over what do you think what would happen if we actually didn't trap the function in the beginning. So there is no definite limit that is trapping g of x. Well, basically what would happen if there was no trapping is the following. We still have our h of x function, as you can see, and we still have our f of x function, as you can see. But our g of x isn't necessarily defined to be in between f of x and h of x. So that means g of x can be anywhere. So as x approaches point A, for these two functions, it must be the same as it approaches point L. But in this case, g of x doesn't have to be. G of x could be something like this. So when it approaches point A, it doesn't have to be anywhere near where point L is. That's also why it's important to trap your functions. Let's move on to another example. Now, let's move over to proving a limit as theta approaches 0, sine theta over theta. Okay, so let's get a better understanding of this by graphing it on Cartesian plane. So let's make 3 Cartesian planes like we did before. Let's just create Cartesian planes. Okay, here we go. And I'm going to create a unit circle in each of them. Please excuse my poor circle drawing skills. I'm not the best. Okay, so let's quickly draw some triangles. So this here would be point P. Simple enough. So point P would just be cosine theta in brackets sine theta. Okay, and now we're just going to draw a line down. This imaginary line. And a line down here. Now let's move on to this triangle. I'm just going to draw point P and just directly to there, creating this little pizza slice shape. Finally, we're going to be creating point P here. Extend to the line all the way up here. Actually exceeding the triangle. Looks weird, trust me. So right away I can tell you this much by just looking at the graph, that this area is less than this area because we're now incorporating this little section of the triangle. Or in this case, it will be greater than this because, well, we're going beyond those unit circles. So I can just confidently say area 1 will be less than equal to area 2, which also will be less than equal to area 3. So let's actually define the areas. Area 1, in this case, can just be equal to base times divided by 2. So that's what the area of a triangle is. In this case, our base would just be 1 because that is the simple radius of the unit circle, and it goes to the extent. So just 1. And our height, in this case, as you know, sine, cosine, and we know y coordinate is sine theta, so it must go up to sine theta, and then over 2 is equal to area 1. In other words, area 1 is equal to sine theta over 2. Next, area 2. Area 2 is a little bit more confusing. So here we have the arc length incorporated, so we're going to have to be going for the entire circle over pi r squared, just because we're looking at a certain area of the circle, and then we also need to incorporate theta. Sorry, I just realized I need to draw theta, theta, theta. So in this case, we'll have theta over the area of 2. That is how we would find the area of this. So we can actually simplify this because we know our radius is just 1. So 1 to the power 2 is just 1, and then we have 2 pi over pi, cancel the pi's. It will just then be equal to 2 is equal to theta over area 2. Area 2, we can just simplify this to isolate for area 2. That would give us theta over 2. And then finally, area 3. Area 3 would be equal to just the same way, base times that divided by 2, since it's a normal right triangle. Area 3, if we know the base is just 1, goes up till the end of the circle. And then something different this time is that it's actually exceeding the unit circle. It won't be sine this time because it's actually going past the unit circle, hence it'll be tan theta. Same thing, area 3 will now just be equal to tan theta over 2. Sorry, over 2. Now we can put all these values back into the original thing. So we have sine theta over 2 must be less than equal to theta over 2. This must be less than equal to tan theta over 2. Now let's actually try to solve for theta. In this case, we can just simplify this side. So we have sine theta over 2 must be less than equal to pi over 2. This side we must have theta over 2 must be less than tan theta over 2. Okay, let's work on this side first. In this side, we can isolate for theta by multiplying both sides by 2. So multiply both sides by 2. We will now just have sine theta is less than theta. And this is where I should mention something quite important. Theta cannot be less than 0. It can be equal to 0, but it cannot be less than 0. Oh, sorry, it cannot be less than 0. Simply put, this is because if we have 0 in our denominator, it will simply just result in the entire function being undefined, and we can't have that. And if it was lower than 0, then that would cause even more problems because sorry, it'll be a negative, and that will result in the sign flipping, and we don't want that. So let's just once again do this, where we will be now taking this to the other side. So it'll just be now sine theta over theta is less than equal to 1. Great. Now let's move on to the other side, where we have this. It's going to be a little bit more complex, so we can right away multiply both sides by 2. So that leaves us with tan theta, and tan theta can just be rewritten as sine theta over cosine theta. This now can be just taken to your side, so cosine theta multiplied by theta is less than equal to sine theta. And we can just cancel out the sine thetas on both sides. So just equal to cosine theta is less than equal to sine theta over theta. Perfect. Now let's combine these all back in a single function. So sine theta here, as we have in our middle, sine theta over theta must be less than 1. Must be less than 1. Or sorry, less than equal to 1. But in this case, it must be greater than cosine theta. Right here. Perfect. Now, we're looking for the limit as theta approaches 0. So we can now substitute 0 into the function. Cosine 0 can just be simplified as, so since we know that as cosine theta, so if cosine at 0 degrees will just be equal to 1. So we can just rewrite it as 1. So that would mean 1 is less than equal to sine theta, or theta is less than equal to 1. Here we have now just trapped the function in between 1 and 1, so we now know that, so let's quickly rewrite this. So limit as theta approaches 0 for sine theta over theta, it must be equal to 1. Thank you for taking the time to watch this video. Bye.